Hello everyone. In this session we will discuss one problem on the frame. Okay, so this is the first problem of frame on kanis method. As you see on the board, I have written the frame. Here we have a portal frame. To the specific, it is a symmetric frame. Why I am saying it is a symmetric frame? See, the column AB and the column CD, they have got a same height, same support condition, even the I value is same. Even though I value for the beam, it is different. When you cut the entire frame exactly at the center, the frame, it is mirror image to each other. The both parts of the frame, they will be mirror image to each other. Whenever you see the mirror images, then those frames we can say they are symmetric in the nature. When the frames are symmetric in the nature, they doesn't undergo the lateral sway. So here, based on this symmetric concept, I can say that the given frame, it is not undergoing any lateral sway. So here I am not going to use the sway component into the analysis, right? So what we need to do here is we need to analyze this portal frame using kanis method, and we need to draw the shear force and bending moment diagrams. So we need to analyze it, analyze the frame by kanis method. Then we need to draw the SFD and BMD. So these are the two things which we need to draw at the end of the analysis. Okay. So here what I am going to do, I am going to straight away implement the kanis method on the frame. There is no deviation of the procedure what we have discussed in the previous sessions, as we are not considering the sway component. Okay. Let me start with the analysis. Solution. As we have already studied, the first step, it is always the estimation of the fixed end moments. Fixed end moments, even we call them as FEM. Okay. All right. Now you can see the frame where the member AB, it is of 3 meter in height, and member CD, it is also 3 meter in the height, but on member AB and CD there is no loading. There is no loading. So straight away I can write the fixed end moments, that is MFAB equals to MFBA is equals to 0, as there is no loads on the member AB. Similarly, the member CD, on member CD also no load, so MFCD equals to MFDC is equals to 0. The fixed end moments for these two members, they are 0. The only member which carries a load is a member BC. So for this BC member, we need to determine the fixed end moments. That is MFBC is equals to, as the load is UDL, WL square by 12 minus, here W is 40 kilonewton into span is 6, so it is 6 square divided by 12, which gives you a value of minus 120 kilonewton meter as the fixed end moment, right? Similarly, the MFCB, it is plus WL square by 12, so here it is plus, the load is 40, span is 6 square divided by 12, so this is plus 120 kilonewton meter. So these are the fixed end moments for the frame, right? So this completes the step number 1. The second step, it is as usual we need to determine the relative stiffness and the rotation factors. For that we all know we have to prepare a table, right? Step 2, relative stiffness, that is the value of K and rotation factors. Okay. For this, I need to prepare a table where we can calculate the rotation factors. So first of all, we need to note down the joints, then we need to note down the members, then we have to work out the relative stiffness, that is the value of K based on the far end condition of the member. Then we need to note down the total stiffness at any joint. Then we can work out the distribution factors. Then at the last we have to work out the rotation factor U, it is equals to minus half of the distribution factor, or else we have one more formula, that is minus half of K by summation of K. So by any of the method you can work out the relative stiffness. Now here you can see from the given loading diagram, what I can see, there are two intermediate joints B and C. A and D are the ends, so I am not calculating the relative stiffness or the rotation factors for those two. Now at joint B we have two members, one is BA, another one is BC. Similarly at a C joint we have CB and CD, right? Now for BA member, A is far end and it is fixed in the nature. So for fixed nature, we know the relative stiffness, it is I by L. Here I value is I, length is 3 meter, so it is I by 3, that is 0.33 I is the relative stiffness for the member BA. Now for BC member, B is near and C is far end, so here C, it is an intermediate support or it is an intermediate joint. So we know that in the structural analysis we consider all the intermediate joints as the fixed one. So here also the relative stiffness is I by L. Here the I value is 3I and L is 6. So this is 0.5 I. Similarly for BC member, B is far end and it is fixed. So it is I by L, 3I by 6. This is also 0.5 I. And lastly for CD member, C is near end and D is far end. So here far end is fixed. So for fixed far end, the relative stiffness is I by L. So here I value is I, L is 3 meter, this is also 0.33 I. Okay, once we estimate the relative stiffness, next we need to go for the estimation of the total stiffness at any joint. For B joint we have two members and the total stiffness it is 0.83 I, and similarly at the C joint 0.5 plus 0.33 it is 0.83 I. So these are the total stiffness at joints. Once we have the relative stiffness and the total stiffness, we can calculate the distribution factors or else we can directly calculate the rotation factors. So it is our practice to calculate the distribution factor, that is distribution factor is equals to k by summation of k, k by summation of k. K is relative stiffness of each member and summation of k is total stiffness of the members at any joint. Here we will get 0.4 as the distribution factor, and similarly 0.5 by 0.83 we will get as 0.6, again 0.5 by 0.83, this is also 0.6, 0.33 by 0.83, it is 0.4. Okay, once we estimate the distribution factors, then we need to go for the calculation of rotation factors. Rotation factors is equals to minus half of the distribution factors. So this is minus 0.2, minus 0.3, minus 0.3 and minus 0.2. So these are the rotation factors, right? So this completes the calculation of the rotation factors. So here what we have done, we have gone with a table where we can estimate the relative stiffness of the each member depending upon the foreign conditions, and from the relative stiffness we have estimated the distribution factors and the rotation factors. So these rotation factors are useful in calculating the rotation contributions in the next step, that is in the step kanis table. Step number 3, kanis table, right? So here what I am going to do, I am going to represent the kanis table as good as like the frame. Just we will be replacing the joints by the boxes. This is member AB and this is joint B. This is member BC. This is joint C and this is member CD. A joint, B joint, C joint and D. So here in the boxes I am going to write one more small box for the provision of writing the sum of the fixed end moments at any joint, right? Okay. Now once we prepare the kanis table, then next we need to write the fixed end moments which we have calculated. So fixed end moment for member AB, that is MF AB is 0, MF BA is also 0, and MF BC as per our calculation it is minus 120, and MF CB it is plus 120, MF CD and MF DC they are 0, right? Apart from this we have calculated the rotation factors. Rotation factors, it is minus 0.2, this is minus 0.3, this is also minus 0.3 and this is minus 0.2, right? Now if I see the algebraic sum of rotation factors, algebraic sum of fixed end moments, that is 0 minus 120, so this will be minus 120, and 120 plus 0, so this is plus 120, right? So these are the fixed end, summation of fixed end moments, right? Now we have to go for the calculation of rotation contributions. So we know the formula for the calculation of rotation contributions. So rotation contribution m dash is equals to, it is rotation factor u into algebraic sum of fixed end moments, that is mf, plus algebraic sum of far end rotation contributions. So this is the formula, right? So based on this, we need to estimate the rotation contributions. Okay, starting with m dash AB. Okay, m dash AB, it is equals to, you can see here, the rotation factor, it is minus 0.2 into the algebraic sum of fixed end moment is minus 120 plus the far end rotation contributions. For B joint, these are the far end rotation contribution, that is m dash BA, sorry, m dash BA, this is m dash AB, this is m dash BC, m dash CB, m dash CD, and m dash DC. Right. Now, for B joint, m dash AB and m dash BC, these are the far end rotation contributions. That is, these will be contributing the rotation values. Now similarly, for C joint, m dash CB and m dash DC, these are the far end rotation contributions. They will be having influences at the rotation contributions of the B joint members. Okay. Okay. Now this lines, they shows the far end rotation contributions. Okay. See, for the B joint, the far end rotation contributions are m dash AB and m dash CB, which I have shown, that is, these rotation contributions influences the rotation contributions of m dash AB and m dash BC. And similarly, for C joint, the far end rotation contributions are m dash BC and m dash DC. These two rotation contributions, they influence the rotation contributions of m dash CB and m dash DC. Now with the help of this, let us calculate the rotation contributions. M dash BA is equals to the rotation factor. Rotation factor is minus 0.2 into the sum of fixed end moments. Sum of fixed end moments is minus 120 plus the far end rotation contributions. The far end rotation contributions are m dash AB, which is 0, m dash CB, which we have not calculated yet, so it is also 0. So it is 0 plus 0. This gives us a value of 24. It is a 24 kilonewton meter. So this is 24, right? Similarly, the next rotation contribution, that is m dash BC, is equals to rotation contribution, that is minus 0.3 into the algebraic sum of fixed end moments, that is minus 120 plus the far end rotation contributions 0 and 0. So this gives us a value of plus 36 kilonewton meter, which I am going to represent here, 36, right? Next, the rotation contributions at the joint C, that is m dash CB. M dash CB is equals to the rotation factor. Rotation factor is minus 0.3 into the rotation, sorry, algebraic sum of fixed end moment, it is plus 120 plus the far end rotation contributions. For C joint, m dash CB and m dash BC and m dash DC, they are the far end rotation contributions. M dash BC, it is plus 36, m dash DC, it is 0. So this gives us a value of minus 46.8 kilonewton meter, which I am going to write here, minus 46.8. Similarly, the last value m dash CD is equals to rotation contribution. So rotation factor minus 0.2 into the fixed end moments plus 120 plus 36 plus 0. This gives us a value of minus 31.2 kilonewton meter, which I am going to represent here, 31.2. Right. So this is the first cycle. Right. We need to keep on repeating such cycles until we get the same values. Okay. So let me go with the second cycle, where, as we know, in the second cycles there is only change in the far end rotation contributions. Remaining, they will remain as it is. Okay. So now here, for the calculation of the rotation contribution m dash BA, it is rotation factor minus 0.2 into minus 120, that is algebraic sum of fixed end moments, plus the far end rotation contributions. M dash AB will remain 0 plus M dash CB, it is minus 46.8 now. It is minus 46.8. So this gives us a value of 33.6 kilonewton meter. So which I am going to represent here, 33.6. The next value here also, it is plus 0 minus 46.8. This gives us a value of 50.04 kilonewton meter, 50.04. And similarly for the M dash CB, the rotation factor minus 0.3 into the fixed end moments plus 120 plus the far end rotation contributions, that is 50.04 plus 0. So this gives us a value of minus 51.01 kilonewton meter. So this I am going to write here, minus 51.01. The next value, that is m dash CD, it is also same. Inside the bracket the values will remain same, 50.04 plus 0. This gives us a value of minus 34.01 kilonewton meter. So this is minus 34.01 kilonewton. If you keep on repeating these cycles, you will get the rotation contributions in the next cycle as 34.2, 51.3, 51.30, then 51.29, 51.29, then 34.26 minus 34.26. These are the rotation contribution values for the third cycle. And if you repeat one more cycle, as see we have not get the same values, so we need to keep on repeating these cycles until we achieve the same values. If you repeat one more step, you will get 34.28, 51.42, 51.42, next minus 51.43, minus 51.43, next minus 34.28. Now still you can see the values, they are not same. It means we need to go for one more cycle where we can expect the same values. If you go for fifth cycle, you will get the same values. In the fifth cycle, you will get 34.28, 51.42, minus 51.43, minus 34.28. So these we will get the same. So when we are getting same, we can say these are the final rotation contributions which can we use for the estimation of the end moments. Right. So here in this session I have shown only the calculation of 2 cycles. The remaining 3 cycles I have written directly. Please do the calculations and cross verify the values. With these rotation contributions, we can go for the estimation of the final end moments. Right. The final end moments, that is step number 4. Step number 4. Step number 4. Final end moments. That is MAB is equals to, it is MFAB plus 2 times of the M dash AB plus 1 times of the M dash BA. So using this formula we can estimate the final end moments. The final end moments, here you can see MFAB is 0 plus M dash AB. So M dash AB is also 0 plus M dash BA. M dash BA as per our calculation it is 34.28. So it is 34.28 kilonewton meter is the final end moment. Similarly, if we calculate the values of the other end moments, that is MBA, it will works out to be 68.68. 68.68 kilonewton meter, and MBC it works to be exactly equal and opposite, that is it is minus 68.68 kilonewton meter. Please verify. MCB it is plus 68.68 kilonewton meter. MCD it works to be minus 68.68 kilonewton meter, and lastly MDC it is minus 34.28 kilonewton meter. So one thing what I can say here is, if you observe the final end moments very carefully, you can make out that they are equal and opposite. See here, the MAB as per our calculation it is 34.28. It is clockwise. 34 means it is a clockwise. So here I will represent it as clockwise. 34.28 kilonewton meter. MBA again it is clockwise. Okay. So this is 68.68 kilonewton meter, whereas MBC you can see it is minus 68.68. So it means it is an anti-clockwise moment. 68.68 kilonewton meter. MCB it is plus 68.68 MCD minus 68.68, minus means it is anti-clockwise in that direction. 68.68 kilonewton meter, 68.68 kilonewton meter, whereas MDC it is minus means it is anti-clockwise. This is 34.28 kilonewton meter. Now see here, it is clockwise 34.28, anti-clockwise 34.28. Clockwise 68.68, anti-clockwise 64.68. It is anti-clockwise, clockwise. So whenever we come across with the symmetric frames, the bending moments developed at the ends of the member, they will be like a mirror image. They will be equal in the magnitude but opposite in the direction. So this symmetric concept, it is very, very helpful in solving the symmetric problems, because we can cross verify the answer there itself. If you are getting different values for a symmetric frame, it means we have gone wrong somewhere. Okay? So with the help of these values, we can go for the further calculation, that is support reactions and the maximum bending moments. Okay? Now, step number 5, support reactions and maximum bending moment values we need to work out, right? So for this, what I am going to do here is I am going to draw the free body diagram of each span separately. Let us say this is member AB. For this member AB, we don't have any loads, but we have the external moments. So I am going to represent those external moments as it is. This is 34.28 kilonewton meter, and this one is 68.68 kilonewton meter. The span is 3 meter. So here what I am going to do, I am going to assume the directions of the reactions as like this, RBA and RAB. So we need to determine the support reactions here. So for determining support reactions, what I am going to do, I am going to implement the moment condition first. So if I take the algebraic sum of moments of all the forces about point A and equating it to 0, then so with respect to point A, so this is a clockwise moment 68.68 minus this is an anti-clockwise moment, so 34.28, and this reacting components creates an anti-clockwise moment, so minus RBA into its perpendicular distance is 3, equating it to 0. So RBA, we will get RBA as 11.42. So 11.42 kilonewton, so which is acting in the negative axis, right? So this is one reacting component. Similarly, if I go for the another equilibrium condition, that is summation of horizontal forces must be equals to 0, then you can see RAB, it is acting towards the positive x-axis, and RBA, it is acting towards the negative x-axis. Apart from this, we don't have any other loads. So RAB, it is equals to the exactly same value kilonewtons, but it is acting towards the positive x-axis, right? So this is something about the AB member. Similarly, we need to repeat it for the next member, that is for member BC. So for if I draw the free body diagram of member BC, this is BC. On BC member, we have a UDL which is of magnitude 40 kilonewton meter, and at the ends we have the end moments. Both are same, that is 68.68 kilonewton, 68.68 kilonewtons. Let us say the reactions are RBC and RCB. Here the advantage is, you can see at both ends, at end B, at end C, we have the moments, but they are equal in the magnitude and opposite in the direction. So their effect will be automatically neutralized. Now, to calculate the support reactions, if I impose the moment condition, that is algebraic sum of moment at point B must be equals to 0, then you can see here this 40 kilonewton, it creates a clockwise moment. 40 into the span is 6 meter, 6 into 6 by 2 minus RCB into 6 equals to 0. See here, I am not considering the moments. Plus 68.68 minus 68.68, ultimately that will be 0. So no need to consider those values for the calculation. So straight away you will get RCB. RCB you will get it as 120 kilonewton. You get it 120 kilonewtons. And if I impose another equilibrium condition, that is summation of f of y is equals to 0, then you can say it is RCB plus RBC minus 40 into 6 equals to 0. So we will get RBC as also 120 kilonewtons. RBC is also 120 kilonewton. And straight away I can say that the maximum positive bending moment will occur exactly at the center. Let us say point E, which is at a distance of 3 meter. So exactly at the 3 meter the maximum bending moment will occur. So straight away you can calculate the bending moment exactly at the center. Bending moment at E, that is ME, is equals to, you can consider the left portion. If I consider the left portion, on the left side we have RBC, which is creating a clockwise moment. So it is 120 into 3 minus, we have this load minus 68.68. Okay. Then we have UDL, which is also creating an anticlockwise moment. So it is 40 into 3 into acting at a distance of 3 by 2. Hence we get ME as 111.44 kilonewton meter. So this is the maximum bending moment. Now similarly for the span CD, that is the vertical member CD, if you calculate the end moments, they will be exactly same but opposite in the directions. See, if I consider the vertical member CD, let us say this is C, this is D. For CD member, I will assume this as RCD and I will assume this as RDC. We have two end moments. One is 68.68 kilonewton meter. Another one is 34.28 kilonewton meter. So here if you do this, you will get the RCD as 11.42 kilonewton, which is acting towards the positive x-axis, and you will get RDC as same 11.42 kilonewton, which is acting in the negative x directions. I hope you can able to do this, right? So with the help of these values, you can draw the shear force and bending moment diagrams, right? So please try to draw the shear force and bending moment diagram, as I am not going to draw those because we have done it for many members. Please do it, and make sure that whenever you are drawing the bending moment diagrams for the frames, you separate all the members and draw the bending moment diagrams and shear force diagrams separately for each member. Thank you.